All right, let's dive in. Today, we are going deep, deep inside the Java virtual machine. We're going to explore memory, the JIT compiler, garbage collection, and threads, all to build a really solid mental model of how your code actually runs. By the end of this, you won't just be writing Java, you'll understand the machine that you're commanding. Let's get started. So think about it. You spend all this time writing .java files, crafting perfect logic, building out features. But have you ever really stopped and asked yourself, what actually happens the second I hit run? What's going on under the hood? That is the big question we're going to answer today. And we're going to do this with a clear roadmap. We'll start by figuring out what the JVM really is. Then we'll look at how it runs code, we'll map out its memory, understand how it cleans up after itself, see how it juggles multiple threads, and then, the best part, we'll put it all together into a new, powerful mental model. Okay, first things first. Before we can build up a new understanding, we have to tear down an old one. We're going to start by correcting one of the most common and, frankly, most limiting misunderstandings people have about the JVM. You know, if your mental picture of the JVM is just a box with a heap for your objects and a stack for your method calls, you're missing out on the most interesting part of the story. That's a static view of what is actually a very, very dynamic system. The reality is so much cooler. And here's the key. The JVM is an active runtime system. It's a seriously sophisticated program all by itself. Its job is to manage the entire lifecycle of your application, from loading your code to optimizing it to managing all the memory all the way to shutting it down. It's not a container. It's a manager. Okay, and here is the first really big shift in perspective you have to make. The JVM actually has no idea what to do with your beautiful Java source code. It doesn't speak Java. It speaks its own, very specific language. And that language is called bytecode. See, when you compile your .java file, you don't get machine code, you get a .class file. And that file is full of these instructions. This is the secret sauce behind Java's write once, run anywhere promise. You write Java, you compile it to this universal bytecode, and then basically any machine on the planet that has a JVM can understand and run it. And the power of bytecode is that it's actually really simple. It's based on a concept called a stack. Just picture a stack of plates. Every operation is a simple little step. You load a value, which is like putting a new plate on top. You store a value by taking the top plate off. You invoke a method, and eventually you return. It's this simple sequence that forms the basis for everything your Java application does. Okay, so we know the JVM runs bytecode, but how? How does it actually do that? Well, it turns out it has two different ways of operating, a kind of tag team approach that is central to how it performs. When your application first kicks off, the JVM uses something called an interpreter. It just reads the bytecode one line at a time and executes it. This is great because it gets your application up and running super fast, but it's not the most efficient way to run code that gets used over and over again. And for that, the JVM has an ace up its sleeve, the just-in-time or JIT compiler. This is where the real magic happens. So how does it know what code to give to the JIT compiler? That's the job of the HotSpot technology. Think of it like a profiler that's always running, watching your code execute. It's looking for these hotspots, methods or loops that get called all the time. Once a piece of code gets hot enough, HotSpot flags it and the JIT compiler jumps into action. It takes that bytecode and compiles it on the fly into highly optimized native machine code that can run incredibly fast. And that right there, that is the entire performance philosophy of a modern JVM. You have this initial warm-up period where everything is being interpreted and HotSpot is just gathering data. But then, as the JIT starts compiling those hot paths, the application's performance just skyrockets. It's a trade-off, a slightly slower start for a much, much faster finish. All right, so we know how the code runs. But where does all the data, the stuff your code creates, actually live? To get that, we need to draw a map of a JVM's memory. So if we look beyond just the simple heap and stack model, there are a couple of other critical areas we need to know about. Of course, you have the heap, where all your objects are, and each thread gets its own private stack. But you've also got the metaspace, which holds the blueprint of your classes, and the code cache, which is where the JIT compiler stashes all that super fast native code we were just talking about. Let's zoom in on metaspace for a second. This used to be called the permanent generation or permgen, and it lived inside the heap. The big news is that in Java 8, it was moved out of the heap and into native memory. And this was a huge deal because it pretty much solved those dreaded permgen space errors and lets the JVM be way more flexible with loading and unloading classes. So metaspace handles the what, the structure of our code. But what about the actual data, the objects we create while our program is running? For that, we need to turn to the most famous part of JVM memory, the heap. Every single time you type the new keyword, the object that gets created ends up here. And it's not just one big messy pile, it's actually highly organized. Every new object's journey begins right here, in a space that is perfectly named Eden. This is the nursery for all new objects. When you write new my object in quotes, the JVM carves out a little spot for it right here in Eden. Now, every so often, a quick cleanup process called a minor garbage collection sweeps through Eden. Any object that's no longer being used just gets wiped out. But the ones that are still needed, the ones that are still referenced somewhere, they're the survivors. They get moved to a special survivor space. They've passed their first test. An object might bounce between these survivor spaces a couple of times, but if it keeps surviving cleanup after cleanup, the JVM eventually makes an assumption. It says, okay, you're probably important. You're going to stick around for a while. And it promotes that object to the final area, the old generation, sometimes called the tenured space. Objects here get checked for cleanup way less often. So why? Why go through all this trouble with Eden and survivor spaces and promotions? It all comes down to one simple but incredibly powerful observation about how programs work. It's called the weak generational hypothesis, and it just means that most objects you create have a very short lifespan. By separating objects based on their age, the JVM can focus most of its cleanup effort on Eden, where most of the trash is, which makes the whole process way more efficient. This whole idea of a structured heap and these cleanups, well, that leads us right into our next big topic, the process that makes Java so safe and powerful. We're talking about garbage collection. Let's trace the complete circle of an object's life. The life cycle is pretty straightforward. First, an object is created and it's placed in Eden. For a while, it's in use, which just means some part of your running code is holding a pointer to it. Then comes the most important moment. It becomes unreachable. This means there are absolutely no more active references pointing to it from anywhere in your application. It's now officially garbage. And the next time the garbage collector runs, that memory is getting reclaimed. So how does the GC actually find the garbage? Well, at a high level, it's a three-step dance. First is the mark phase. The GC starts at the roots of your application, like your main thread, and follows every single reference from one object to another. Think of it like walking a giant web. Everything it can touch, it marks as alive. Then comes the sweep phase. Anything that didn't get a mark is considered garbage and is swept away. And finally, some GCs will do a compact phase, where they shuffle all the surviving objects together to keep the memory nice and tight. We've got a pretty good handle on how code runs and how memory gets managed for a single line of execution. But let's be real, modern applications are all about concurrency. So let's connect our memory model to the world of threads. This is the single most important rule to burn into your brain about concurrency in the JVM. When the JVM fires up a new thread, it gives that thread its very own, totally separate, totally private stack. One thread cannot see or touch another thread's stack. It's a fundamental wall of separation. And every time a method gets called on that thread, a new stack frame is pushed onto its stack. This frame is like a private little workspace for that one specific method call. It holds all of its local variables, a temporary area for doing calculations, and crucially, the return address so it knows where to go back to when it's done. And this brings us right to the heart of the entire challenge of concurrency. Because each thread has its own private stack, the stacks themselves are inherently thread-safe. A thread's local variables are its own business. But the heap is a shared public space. It's a free-for-all. Any thread can have a reference to the very same object on the heap, and that is where things get dangerous. So how does the JVM prevent chaos? Through synchronization. When you use the synchronize keyword in your code, you're essentially telling the JVM to put a lock on that object. It's like putting up a one-at-a-time please sign. Any other thread that comes along and tries to access a synchronized part of that same object has to wait in line. It's the JVM's way of enforcing order in the shared world of the heap. Phew! Okay, we have covered a ton of ground. Bytecode, JIT compilers, memory maps, GC, threads. Now for the payoff.
Let's assemble all of these individual pieces into one complete, cohesive mental model that you can use every day.
First, let's learn to speak the JVM's language. These common errors aren't just frustrating bugs, they are signals. They're the machine telling you exactly what's wrong. A Stack Overflow error? That means a specific thread stack got way too deep, probably from runaway recursion. Out of memory error? The shared heap is full. GC overhead? That means the garbage collector is working way too hard and not getting much done. Understanding the internals lets you decode these messages instantly. So here it is, the whole journey, start to finish. Your Java code becomes bytecode. The JVM loads it and starts interpreting it right away. As it runs, the HotSpot engine is watching, and it hands off the busy parts to the JIT compiler to turn into lightning-fast native code. As your code runs, objects are born in the heap's Eden space, while each of your threads does its work using its own private stack. And the whole time, like a diligent housekeeper, the garbage collector is running in the background, keeping the heap clean. That is the machine you are commanding. So why does any of this matter? It's not just about passing interviews. It's because knowing what's happening under the hood transforms you from someone who just writes code that works to someone who writes code that performs brilliantly. It's a fundamental piece of mastering your craft. So the next time you type new, you'll know exactly what journey that object is about to take. The only real question is, what are you going to build with that new power?